The following is a production of Texas Lutheran University. For more information, please visit tlu.edu.
Before I introduce our speaker, I need to thank a couple people for making this all happen. First, I need to thank the Brown Endowment for paying for the visits. I appreciate that. Special thanks go out to Sarah Story for all the advertising that she did, her and her marketing staff, and Terry Price. Thank those guys for putting this all together. I also want to thank President Dorsey and his wife Michelle for being here. They're there in the back. And again, I want to thank all of you for showing up. This is great. All right, so I'm here to present Timothy Gay. He is from the University of Nebraska. He got high school in Phillips Academy in Andover, Massachusetts, where he was friends with Bill Belichick, who was coach of the New England Patriots. In 1975, he got his BS in physics from a small school, Caltech. Thank you for laughing, I appreciate that. He actually spent a year as a grader for Richard Feynman, who is a Nobel Prize winner in physics in 1965. University of Chicago, he got his PhD in experimental atomic physics in 1980. He was a lecturer at Yale. He was a faculty member at University of Missouri-Rolla, and 1993, right? Yes. Started at University of Nebraska-Lincoln, where he is today. His research is on electron scattering and particle physics, as well as football physics. Tomorrow at 1 o'clock in this room, hopefully not all of you will be here, he'll be giving a research talk about his research at Nebraska. His football work has shown up in a lot of places, many of which he'll talk about today. The biggest thing for me, when I was in grad school, I went to the University of Nebraska, and I'm a big reader of ESPN.com. And I was reading an article about collisions and concussions with helmets, and there's a little blurb about concussions and the physics of it, and it was Tim Gay who wrote that. And I was just like, wow, that's cool. So anyway, without further ado, Timothy Gay.
Wow, I'm amazed. Thank you so much for coming out. I especially appreciate the invitation to come down to TLU. I've been very impressed with the facilities and the faculty. We've had a good time, so I'm looking forward to tomorrow. It's been a great visit. What I want to tell you about tonight is football physics, but specifically focused around some pieces that I did for Husker Vision. Husker Vision being the audio-visual arm of the athletic department at the University of Nebraska. And basically it all started in 1999 when the director of Husker Vision thought it would be interesting to put something up on the big jumbotrons in Memorial Stadium that showed something maybe a little more academic than, cute kids asking their favorite player what their favorite color was or something like that. So I thought, well, this is an academic institution and there's a lot of physics and football. Maybe we should do something like that. So he sent a producer over to the physics department, and she walked into the front office and said, do you have any physics professors that love football and are shameless self-promoters? And they all stood up and said, well, that would be Tim Gay. So the rest is history. She came down and talked to me, and she didn't have to sell me very hard. I was very, very interested from the get-go. And what I want to tell you about tonight are some of those pieces that we did. I actually have a kind of a history with football. I did play football in college, on the team that was so notoriously inept that we got written up in the joke column of the Wall Street Journal. You know you're in trouble when you appear in the central column of the Wall Street Journal. And I won't go into detail, but there's just a couple of paragraphs that have burned themselves into my memory. Some of you in the back can't read this. The one that really got to me, at football factories like Ohio State, Tens of thousands of dollars are spent in recruiting high school superstars, and networks of hundreds of alumni help ferret out and woo likely prospects. At Caltech, recruiting consists of Coach Gutman lurking in the bushes, while students play intramural touch football and jumping out periodically to try to persuade promising youngsters to sign up. Most don't. Well, not being the sharpest knife in the drawer, I signed up, and I actually had a great time playing in college. It was a wonderful experience. I have to admit, though, to some ambivalence. When Kay, the producer, came over to talk to me, I thought, you know, if I start doing this, if I start talking about the physics of football to 85,000 fans in Memorial Stadium, I will be taken less seriously as a scientist. That's kind of shown here in this. This is back when some of you remember Carl Sagan when he was big and was popularizing science. He was sort of the latter-day Brian Greene. And here's two cranky old professors of physics. Actually, one of them looks remarkably like one of my colleagues. One thing I'll say for us, Meyer, we never stooped to popularizing science. And I thought, gee, if I do that, if I popularize science, I will be taken less seriously. I strongly disagree with that viewpoint, because I think it's crucial for scientists to explain to the public, who are, after all, paying the bills, why what they do is interesting, why physics, in my case, is important. And one thing I've learned in teaching over the years is that if you want to engage your students, if you want to get across a point, you have to relate it to something that they're really interested in. And you know, one thing we're really interested in Nebraska, almost as much as you guys are in Texas, is football. And so I thought, okay, if I can relate this to football, this will work out well. So it's been a wonderful experience. I went over and we talked about what was required, and we talked about what might be a good first piece, and I wrote out the script. And I thought, you know, being a naturally long-winded professor, I thought I was being incredibly succinct. And I read the thing out, and it came in at 4.5 minutes. And Jeff said, no, you have 1 minute to get this idea across. And I thought, holy cow, that's a tall order. And so it's been a real learning experience for me to see how we can actually get across an idea in a short amount of time. So I think now what I want to do is to show you, I'm going to show you a couple pieces to give you a kind of feeling for what we did. So these pieces would show on the big jumbotrons in Memorial Stadium, typically in the second or the third quarter during a timeout or something like that. So here's what we have here. I'm hoping this will work. Yes? We have no sound. Why do we have no sound, Sean?
Today, we're going to talk about momentum. To make an effective tackle or block, a player must have more momentum than his opponent. This is illustrated nicely by a block thrown by John Rood during a kickoff return in the 1978 A player's momentum is equal to his weight or mass times his speed. In this play, Rood weighed 215 pounds and was traveling at about 10 meters per second. Rood's momentum, roughly 1,000 kilogram meters per second, and 3 times that of the Oklahoma player, effectively stops the run. Using Newton's second law, we can calculate the force of the hit to be about 2/3 of a ton. That's gotta hurt. Now let's use some momentum to move the ball down the field and score another touchdown.
So we learned one important thing from this particular video, and that is that I'm not going to be getting an actor's equity card anytime soon. But okay, so let me just show you another one along the same lines here. There we go.
We've talked about Newton's laws in general and the third law in particular. Now let's talk about the second law. It says that force is equal to mass times acceleration. Consider, for example, the Husker offensive line in a 5-man set. The starting line last week against Iowa weighed a total of 1,535 pounds, which is equivalent to a mass of about 700 kilograms, kind of like a small car. These guys have to be able to exert enough force off the line to give themselves an acceleration of 7 meters per second squared. That amounts to a total force for the whole line of almost 5,000 newtons, or 1,100 pounds, more than half a ton. So remember, Tonu, when you run over Missouri today, may the force be with you.
Yeah. Okay, so those were the kinds of things people are saying. But now, I don't want this to be all fun and frivolity. Let's talk a little bit about the physics behind what those pieces dealt with. So when you watch a football game, basically what you're seeing on the field is classical physics, Newtonian physics in action. Sir Isaac Newton, probably the greatest genius that ever lived, developed these laws to describe mechanical action on the football field. For example, he wasn't thinking football, of course, but that's how it boils down. So what are those laws? Well, the first, and this is for all you physics students out there, the first law is mass wants to do what it was doing before. If a mass is at rest, it wants to stay at rest. If it's moving, it's going to keep moving with that speed in that same direction unless I act on it with a force. And you say, okay, well, that kind of sounds right. But think about Newton's day. I mean, think about our own day. What is the natural state of matter? Well, if I, take my foot off the accelerator of my car slows down and comes to a stop. If I'm playing pool and I hit the cue ball, it'll rattle around for a while, and then it'll come to a stop. So it's obvious, it's common sense that the natural state of matter is to be at rest. And this is what people thought in 1600. It's obvious and common sense, and it's wrong. It took a genius like Newton to figure out that the natural state of matter is to kind of keep doing what it was doing before, unless I apply a force to change that state of motion. That's what the second law is about. The second law says, if you have a force, I can then, knowing the mass of the particle, calculate the acceleration. This is the equation, of course, that we use to torture all the high school physics students with. What is the acceleration if you're given the force? But this turns out to be crucial. This is now a mathematical quantification of how we change the state of motion. The third law is basically that if I have two bodies interacting, say two asteroids interacting gravitationally, asteroid 1 attracts asteroid 2 with a gravitational force. It has a magnitude. But Newton's third law says that first body is attracted to the second body with the same amount of force but directed in the opposite direction. So that's the basic idea. So we can then use those concepts, and here specifically the second law, to calculate the kinds of forces that are experienced on the football field. So let's take that hit by Tom Rood in the 73 game. So what I have here, 78 game. So we say that, back. What we have here is some force is equal to the mass times the acceleration. Now the acceleration is equal to the change in speed delta v. We use the Greek capital letter delta to mean change, divided by the change in the time over which that change in speed occurred. So let's consider a big hit. What we've got here is a player, typical football player, 100 kilograms, 220 pounds. In a big hit, if the player is running flat out, he'll change his speed from about 10 meters per second to 0 meters per second. And typical hits in football occur over 200 milliseconds, or about 0.2 seconds. You do the math, you get 5,000 newtons, which is about half a ton. The technical physics term for this is called getting your bell rung. So these are big forces. This is why football is a contact sport. Here's a sort of typical. This is actually the best football picture there is. This is number 51 for the Bears, tackling the entire Green Bay line. Right. Okay, so the forces in football are big. I mean, when two players collide helmet to helmet, basically that's equivalent to getting conked on the head with a 16-pound bowling ball dropped from a height of 12 feet. Making a guy miss is good unless he grabs your face mask on the way by, and then it's essentially like sticking your head in an industrial washing machine. You get the same torque to your neck. They talk about quarterbacks throwing bullet passes, and that's actually pretty right. Brett Favre throws fast passes, and it's essentially equivalent to catching, 10 of his passes is essentially like putting on some bulletproof gloves and catching 40 bullets from a .44 Magnum revolver, the most powerful handgun in the world. So, again, Devin Hester, it makes a hard cut. There's about 800 pounds of force going through his ankle. Okay, so these are big forces. So I talk about this and people say, well, gee, professor, that's great. You're telling us it's better to be a big, fast guy than a slow, small guy. Well, duh. I don't need to take a physics course to know that. And it's true, it is better to be a big, fast guy than a slow, small guy. But there's some subtleties here, and I'd like to kind of try to illustrate a few for you. Let's consider first this little demonstration over here. You guys sitting in front may want to be a little careful. So what I have here is a wood block, weighs about 1.3 pounds. And then I have a lead block, which weighs about 28 pounds. Same volume, roughly. Now I want to do a little experiment. I'm going to take some styrofoam coffee cups that Professor Hilbert and I bought this afternoon at the grocery store. And I want to now just balance these bricks on these coffee cups. And you have to be a little careful about doing this. Here we go. It's pretty good. Okay, and now the problem with this is that if I just kind of set this down, it's going to just squash these cups. So you gotta, careful, very gently. Set it down. Okay. Now I'm going to put this here. And here. Okay, now, the experiment that I want to do is to now take this 2-pound lead mass, and I'm going to drop it on these two bricks. This is, you guys might want to watch. And see which is more effective at crushing the coffee cups. Okay, so I'm going to drop it from the same height in each case. I want you guys to tell me which is going to be more effective. Is it going to be the wood brick or the lead brick? How many say the wood brick? Yeah. How many say the lead brick? Yeah, that's obvious. Okay. So here we go. I almost killed a regent once doing this, Professor kills regent, loses tenure. I can just see that. Okay, so I'm going to drop it from about this height, and here we go. Okay, here we go. Okay. And now, oops, can somebody get that for me? Could you help me there? So, not a lot of damage. There's just some dents there. Okay, thank you. Okay. But now, watch out. Okay, here we go. Same height. Nothing up my sleeve. Here we go. Oops. That didn't work very well. Okay. This is the great thing about doing physics demonstrations. You always disprove the law of physics. Usually when I do this, in fact, the lead brick is not any more effective. Usually it's a lot less effective than the wooden brick. Why is that? Because of the first law. The first law says mass wants to do what it was doing before. And what it was doing before was standing stock still. So the mass of the lead brick is so large that it's not easily accelerated, and so it doesn't scrunch the coffee cups. It did it about the same this time, but I think it was just because I was off a little bit in dropping it. I've never stood up like this and done it before. So again, things aren't quite so obvious. Let's do another demonstration here. So I need some audience members to participate in this. So first of all, I need somebody really big. I mean, okay. So I've got my big person. Okay. Now I need somebody really tiny. Aerospace. Yeah, you're up. Let's go. Okay. Now, I want you to think about Doug Flutie, the quarterback, standing in a pocket, getting ready to throw a pass, and Warren Sapp's coming around the end with a full head of steam, and he cleans Flutie out. Just nails him. Okay. Flutie weighs what? I don't know, 165, dripping wet. Warren Sapp weighs 330, and he can run. He's fast. Okay. So he cleans out Flutie. Who exerts a bigger force on whom? Does Sapp exert a bigger force on Flutie, or does Flutie exert a bigger force on Sapp? Well, we've got a big person and a small person here. So we're going to do the experiment. So what I have here are Newton scales. They're just spring balances. Okay. So I want you to grab this one and make sure you hold it so that people in the audience can see it, and just hook your hand there. You do the same thing, and now we're going to hook the hooks here. Okay. And what I want you guys to do, we have a little tug of war. So you guys stand off like this. Whoops. And I want you to both of you pull so you've got 30 newtons on your scale. Okay, 30. Good. There you go. That's pretty good. Good. You might want to come out here a little. Okay, good. So everybody can see it. Okay. So they're now exerting the same force on each other. Okay. Now what I'd like you to do is pull with, you're bigger, you pull with 50 and you stay pulling at 30. Okay. No, you pull at 30. Come on. You're at 50. You're at 50, right?
Yeah.
Okay, you're at 50. Good. Oh, no, you just get 30. Come on, you guys, pay attention. Okay. They can't do it. They can't do it because of Newton's third law. Let's give them a hand. Good job, guys. Thank you. Newton's third law says that Sapp exerts the same force on Flutie that Flutie exerts on Sapp. Well, why is Flutie the guy that goes flying? Because he's got less mass, so he's more rapidly accelerated. So this is good. We understand this third law now. We've just done the experiment. Everything's good. We got Newton's three laws done. So if that's true, if we understand Newton's third law, maybe you could explain to me how anyone ever wins a tug of war. How does that happen? Okay, so all of these laws that I've been talking to you about are basically due to Newton. And here he is. He said that he stood on the shoulders of a giant, and this is New York, Meadowlands, get it? Yeah, okay, sorry. Okay, let's now do the next topic. This is a piece we ran in the second year. Okay. Can everybody hear okay? Is the sound level okay? Okay. Oops, back. I'm hoping to find, there we go.
Energy, like force and momentum, are important quantities. Football players expend a lot of energy in a game, and this training table is where they get that energy. On game day, these guys eat about 6,500 calories, more than 4 times what an adult sitting on a couch watching television all day would expend. But when the ball is snapped, a tackle firing off the line of scrimmage uses food energy at about 50 times that rate. In the first second of play, both teams combined expend enough energy to lift a pickup 10 yards in the air, enough for a vertical first down. Over the course of the game, both teams do enough work to lift this iron girder used in our new skyboxes more than 1.5 miles in the air. What we learned from this lesson in physics is that football is a very energetic sport.
Hey Doc, that's my food.
We also learned that you don't ever get between a lineman and lunch.
So that guy is Adam Julch. He started for 4 years at offensive tackle for the Huskers. He was a math major, graduated with a 3.95 GPA, got an A plus in my calculus-based physics course. So not all linemen are dumb. Most are, but not all of them. Okay, so what are we talking about there? Well, we're really talking about power, the concept of power. Power is basically defined in physics as being the rate at which I do work. So it's the change in work over the time it takes me to do that work. Work will change the kinetic energy accordingly. We're used to thinking about horsepower typically in terms of rating car engines, and that's a good way to do it. But you also think about watts when you talk about light bulbs. Both are units of power, and 1 horsepower is equal to 746 watts. But a watt is also equal to another unit of energy, which is food calories. The problem is there's physics calories and there's food calories. It gets very confusing. But food calories, like there's 170 of them in a can of Coke, food calories per second, 1 watt is about 2 10,000ths of a food calorie per second. We eat food so that we can live, so that we can work. But it turns out that human activity has a broad range of required power. So, I can click, can't I? Yeah, right. So let's consider being a couch potato, sitting on the couch and watching a football game. Basically, just to keep your brain functioning and your heart beating, you expend about 1/7 of a horsepower. You require somewhere between 1,500 and 2,000 calories a day to do that. But humans are capable of much more. Humans are capable of athletic exertion, such as riding a bike up a hill or pedaling a man-powered plane over the English Channel, which requires about 3/4 of a horsepower. They can do that for about 3 hours. So that's impressive. But you can actually get higher than that if you fire off the line. A tackle firing off the line actually is expending about 3,500 watts or 5 horsepower, so like 5 horses or something. You can't do that very long. You can only do it for a couple of seconds. But humans are capable of huge bursts of power. There's another unit floating around here, and that's energy. So I want to talk a little bit about that. This is a graph. I don't want to get too involved here, but this is a graph of the mass of the average offensive lineman in the NFL as a function of year. And we start in 1920 at about 190 pounds, and we go up to 290 in 2000. We're well above 300 now. I think the number is like 305 in the last year, something like that. So basically, we've increased football player mass by about 50% over the existence of the NFL. Players are getting bigger. They're also getting faster. This is a rough estimate of the increase in speed. Now, unfortunately, there aren't 40 times available for NFL linemen. But what you can do is you say, well, linemen are slower than world-class sprinters, but world-class sprinters are getting faster. Linemen are probably getting faster at the same rate. In other words, their percentage increase is probably the same. It's just they're a little bit slower overall. So in terms of world-class sprinters, we've gone in 1920 from about 33.8 feet per second up to 37.2, something like that. Now, if I combine the speed squared and the mass together, I get energy. So I can calculate the energy, essentially the energy that's dumped into the line of scrimmage on any given play in the NFL or by inference in college football or high school football. And what do you find? What you find is basically a doubling of kinetic energy. Let's not worry about the units. Basically, it goes from 3,300 up to 6,300. So almost a 100% increase in the energy that's dumped in to the line of scrimmage on any play. Football is a very violent sport. That's why we love it. If that's true, why aren't more players getting injured? because the injury rate hasn't increased significantly from 1920? And the answer, of course, is that the equipment is getting better. In the old days, shoulder pads, basically you took cotton batting and you put it on your shoulder and then you'd pull your jersey over it. They wore leather skull caps, essentially, for helmets. Now we have very good equipment, and that's the topic of this next video. If I can get it, here we go.
Let's talk about football helmets. A helmet acts to distribute the force of a hit to a player's head over a larger area. A sharp, concentrated blow to the head, if delivered by a large force, can cause serious injury. But it's not the force that matters so much here, it's the pressure. The formula for pressure is force divided by the area over which the force is applied. From this equation, we can see why a carpenter, using a relatively small force, can drive a nail into a board. The cross-sectional area of the nail is relatively small. A helmet distributes the force of the hit over a large area, thus reducing the pressure that the player's head feels. In the same way, the principle of distribution of force allows me to lie down on this bed of nails without significant injury.
So I've gotten more comments on this piece than any other piece we've done. And the comments go something like this. It's kind of disconcerting. People come up to me, they say, how is it you were able to trick the camera into making it look like you can actually lay down on a bed of nails when we know you can't actually do that? I said, you think I'm teasing? You think this is trickery? No, this is physics. But people often just think this is some sort of illusion, a magician's show, of course. So we've got a long way to go in physics education to get some of these basic ideas across. But let's talk about football helmets. I can do this, can't I? Yes. Okay. So how does a football helmet work? Well, here's a football. You know what the N stands for, don't you? Anybody? No. Knowledge. So how does a helmet actually work? The helmet, thank you. Wait a minute, let me come unhooked here. The helmet does distribute the force of a blow because of the hard polycarbonate shell. Basically, I hit the thing and the blow gets distributed over a large area. So it's sort of like an anti-nail, if you will. A nail concentrates force, this distributes the force. But there's another crucial idea here, and that is the padding. I got too many controls. Here we go. The padding inside also protects the player because it essentially lengthens the time of the collision. If we weren't wearing helmets and we had skull on skull, it would be a very sharp, impulsive blow like this. Let's say that my head comes in at 5 feet per second and the guy is standing and not moving. So the closing speed of the collision is about 5 feet per second. The laws of physics tell us that the momentum transfer, which is essentially the green area under this curve, this is now force versus the time of the collision. The momentum transfer is going to be the same whether I'm wearing a helmet or not. But with skull on skull, the collision is very sharp. Whereas if I've got padding, the collision is spread out in time. But remember, physics tells us that the momentum transfer has to be the same, which means that these two areas in green, this one and this one, have to be the same. But since here the time was longer, that means I lower the maximum force. So I lower the force. It's the same principle. If I have an egg and I drop it from 2 meters, if it hits the floor, the cement floor, it'll break. But if I simply put a piece of foam rubber there, it won't break. The change in momentum is the same in both cases. The egg was falling at the same speed when it hit the ground. It came to a stop, but in one case it came to a stop more slowly, so the force that the egg felt in that case was lowered. So it's great to talk about this stuff, but we really, again, ought to do an experiment. And we've got the football helmet. What we don't have is a head. But fortunately, Sean took me over to the practice field today, and I was a bulldog who had an unfortunate accident, and I happened to have retrieved his head, and here it is. I'm just joking. It's not really. Here is a head. He's looking a little disconcerted. And we're going to put this in. Professor Hilbert may need to help me now. We have a little demonstration here with the, if you can just, we're going to see how this works here. So I'm going to take this guy and I'm going to put him in the helmet, like so.
You think it's going to be big enough?
Yeah, I'll see. You guys don't have good clothes on or anything. Are you okay here? Yeah. Okay. I've got his little chin strap on, so he's okay. Okay. And I dare go up here. Yeah, this is good. This is good.
Are you okay?
Yep. Okay, so actually I'm going to go right here. So I can do it. Okay, this is good. Okay, so here we go. Okay, and I drop it, and let's see what happened here. Oops, we have a concussion, don't we? Yeah, there's a kind of an unfortunate fracture here. Yeah, my demos aren't working out so well tonight. We have a small fracture like this. Okay, now, but of course, we want to do this scientifically, and of course, to do it scientifically, we need a control experiment. So I have another head, and of course, if I were really, I'd have used the same thing, but he's already in bad shape. Let's try this one from the same height. Parents, try this at home. Try to convince your kids to wear their bicycle helmets. So, here we go. Same thing, same height. Here we go. Yeah, but his fracture is worse. Sometimes the results are more spectacular than this. Okay. Yeah, let's see. Here we go. Yeah, there we go. Here's our breakfast, Sean. Yeah. Okay. Yeah, not so bad. Okay. So let's see where we are here. Yes. Next topic. Right. Okay. Oh yeah, I remember which one this is. Okay.
Symmetry is an important principle in physics and in football too. Consider the football itself. It has a long axis of rotational symmetry about which it can most easily spin. We all know that a coin standing on its edge will fall over unless it's spinning. In the same way, a football must be spinning for it to be stable in flight. As Eric will demonstrate, a well-thrown football rotates about its long axis of symmetry. Eric's hand puts spin on the ball to stabilize it in flight for maximum yardage. Unfortunately, understanding the theoretical principle of symmetry doesn't guarantee instant success as a quarterback. Hey, Doc, you got a chance to evaluate your arm, and I think you're better suited for the offensive line.
Which is exactly what I played, so yeah. Some of you may recognize Eric. That's Eric Crouch. He won the Heisman Trophy in 2001. So he was a lot of fun. We did 5 of these pieces together, so we had a good time. So what are we talking about here? Basically, you want to stabilize the ball by spinning it like a gyroscope, because that will hold it in the most streamlined attitude, and you do that by basically rolling it off your fingers. Keep in mind that the original football that was used in the first American football game, was the second Yale-Harvard game in 1879, was essentially a rugby ball. But the ball has evolved to something that looks more like this because it's easier to pass and you can put a higher spin on it. So that spin is important to stabilize it. Okay? So, you know, I go out and I give this talk to a lot of different groups. Sometimes I give this to the Cub Scouts or the Girl Scouts. And I take along this little thing. This is a little toy gyroscope to illustrate the effects of spin. So I can put this in here, like so. And I can get it spinning, like so. And then I can balance it on my nose, for example, like so. And fortunately, sometimes it punches you in the face. The scouts love it when it hits you in the eye. They think that's great. To illustrate this, but there's a problem. So I take this out and I show this, to the campfire girls or the Cub Scouts. They've never seen one of these before. There's a real problem, ladies and gentlemen, in American education. Kids aren't getting their hands on real, they're playing video games, for heaven's sakes. They need to be playing with stuff like you can get one of these from Edmond for 79 cents or something. So let's put more of these in the hands of America's youth. Okay, but why do I care about the ball being in a streamlined attitude? Well, let's talk a little bit about the flight of the ball through the air. I don't want to dwell on the math here, but basically air drag is important. If I throw a tight spiral pass, there's about 1.4 newtons of force due to the air drag, assuming sort of nominal atmospheric conditions. But if I kick a tumbling end-over-end kick, then the air drag goes up to about 14 newtons. You say, well, it's just kind of fortuitous that this is 10 times this. That's not anything fundamental. The point is that the darn ball only weighs 4 newtons. So these drag forces can be really significant. That's why a tight spiral is important if you want to throw the ball a long distance. So we did some numerical simulations to try to understand this, and here's one of them. So what we have here is basically a numerical simulation in which we launch the ball at 45 degrees with a 100 foot per second launch, which is pretty fast. Not many people can throw a ball 100 feet per second. In fact, I think you have to kick it to get it going that fast. But if I do this on the moon, in vacuum, well, the moon is bad because the gravity is different. But if I removed all the air from the Earth, it would essentially go about 105 meters. Okay. With atmospheric pressure, there's air drag, and so a tight spiral will go about 85 meters, 82 meters, and a tumbling end-over-end kick will only go about 45 meters. So that air drag has a huge effect. But if you look at the graph a little more closely, you'll see there's actually 2 lines here corresponding to the tight spiral pass. What's the difference? The purple curve is done in Denver, 1 mile above sea level. The yellow curve is done in Foxborough, Massachusetts, essentially at sea level. So there's about a 3 or 4 yard difference due to altitude. So that can be important in a game. You get that same kind of differential with the tumbling end-over-end kick as well. And you think about air drag. Air drag is important. So let's consider another simple experiment. Let's take this book, and I have a piece of 8.5 by 11, a sheaf of 8.5 by 11 papers, and I want to drop the 2 and see which gets to the floor first. Which do you think is going to get to the floor first? The book? Think the book? You may want to rethink this given your answer on the lead brick. Okay. Be the same? Let's try it. Okay, here we go. The book got there first. You were right. Okay, why is that? The reason is, we'll go here. The reason is that essentially the book weighs more. There's more force to accelerate it. The air drag, they both have the same area, essentially. The air drag is about the same, but the book weighs more, so there's more force to accelerate it to the ground. But the acceleration is proportional to the force, and the force is proportional to the mass. So if you do the analysis, you realize if I didn't have any air drag, they should get to the floor at the same time. That's the famous Galileo experiment, or the famous experiment that Alan Shepard did on the moon. A feather and a ball bearing will drop at the same speed when there's no air drag. So let's do that here. So first, Sean, could you pump all the air out of the room, please? And then we'll, no, that wouldn't be a good idea. Don't do that. Okay. How do we remove the air drag? What do you think? Good idea. Let's try it. What do we get now? Ha! They reach at this, the air drag is gone and they fall at the same speed. So again, I'm talking to the Cub Scouts about this, and I show them this picture, and they're looking at it. And the important point here is that 1 in 100 Cub Scout will go home and understand what I've said. But that's okay, because 90 out of 100 will go home and worry about it. And they'll think about it. And that's what we want. We want them thinking. Okay. Okay, what do we got next? Yes, let's talk a little bit. We don't have time to do that video, but let's talk a little bit about sound in the stadium. So, sound is essentially a rating of power, watts, divided by area. And we measure sound in decibels, and it's essentially the log of how much power I have. So we define the threshold of hearing, a sound you can just barely hear with a normal human eardrum, as being 0 decibels. Rustling leaves have about 100 times more power per unit area. So 100, you take the log of that, that's 2, multiply by 10, as per the formula right here, and I get 20 decibels for rustling leaves, about 40 decibels for a buzzing mosquito, 60 for normal conversation. You get up to, for example, an Anthrax concert, and you're at 120. A jet taking off nearby is about 150, and that'll permanently damage your ears on one shot. The loudest stadium in the world is Arrowhead Stadium in Kansas City. And that's got a decibel level in extreme situations of about 128 dB. Notice that the loudest stadium in the world is not a domed stadium. People say, it's a domed stadium, so it's louder. You know that's wrong, because if you stand in a domed stadium and scream, you don't hear an echo. The loudest stadium is an open stadium, Arrowhead. Okay. So, if you're playing against the Raiders in Oakland on Hegenberger Road, it can get pretty loud. Oakland fans are, well, you know how Oakland fans are. And it can become extremely intimidating. Sound is, of course, really, think about Texas A&M. They do a really good job of making a loud environment, and they win some marginal games because of that home field advantage. Okay? But can the sound in a stadium actually affect what goes on the field? And the answer is kind of, sort of not. If you have 70,000 rabid Raider fans screaming for 4 quarters, and they got megaphones and they're directing it down to midfield, you'd actually get about enough energy in 4 quarters to boil a cup of tea. And that's it. Okay. So sound has a very important psychological advantage in football, but in terms of its actual mechanical advantage, there's nothing. Which is really, more than anything else, a testament to how sensitive our ears are. There's another, sound is a wave. It turns out there's another kind of wave that I got interested in a while back, and that is the speed of the wave. When people, stand, whoa, like that. What's it called in Mexico? Hola or something, yeah. So, so what I did, is sit in Memorial Stadium for many seasons. I got season tickets. And when I saw the wave firing up, I would measure its speed. It's just how many seconds does it take it to go around, and you calculate that. And then I would read the paper the next day and find out what the temperature had been on field during the game. And my wife is getting madder and madder at me as I'm doing this. What I've found out is that there's actually a functional dependence on the temperature of how fast the wave goes. And it kind of follows this purple curve with some rather large error bars, to be sure, but it does follow this curve, which is interesting because basically The speed of a sound wave has the same kind of curve. It goes like the square root of the temperature, but the speed of a sound wave goes to 0 at absolute 0, whereas the speed of a human wave in the stadium goes to 0 at about minus 40 degrees C. You think about it, at minus 40 degrees C, which happens to be minus 40 degrees F as well. Would you want to do the wave at minus 40 F? I sure wouldn't. So something else to think about. Okay, so we're almost done. I want to talk just very briefly about some myths that you often hear about in sports, and let's focus them on football. So humid air shortens a football's range. You actually hear that more in baseball. Oh, it's really humid, you know, the balls are dropping, nobody can hit a home run. That turns out to be wrong. In humid air of the same temperature and pressure as dry air, the ball actually goes further. You say, how can that be? And the answer is really quite simple. Water molecules are less massive than the average air molecule. So it's like driving your car through ping pong balls instead of bowling balls. You go further. Okay. This has actually been shown with baseballs. They've shot baseballs out of cannons in different humidity, and the ball doesn't go as far when it's dry as when it's humid. So I don't know where this comes from, but keep in mind, though, my caveat that you have to have the same temperature and the same pressure. So it may be that there's some, atmospheric issues that change those just when, I don't know, it's not clear. But for set conditions, that's not true. Let's talk about turf. Is artificial turf faster than natural grass? Now this is actually was born when people were using tartan turf and astroturf, which is almost obsolete now. I don't know of any place that has those anymore. But this pointed out to me the real difficulty of finding any careful research in the area of sports science. I could find only one careful study where they tried to determine which was faster, astroturf or regular grass. And what they found is that, in fact, astroturf is faster. And this is now what this is just a graph for different kinds of football players, tackles, guards, tight ends, back one, back two, back three. And they did two things. They ran a straight 40 and then they ran a slalom 40. And what they found was that in the slalom and in the straight there was about nominally a 200, 250 millisecond advantage over the course of the run for the astroturf as opposed to the natural grass. So this is now scientific proof that at least astroturf is faster than natural turf. Turns out it's an irrelevant argument because when you now try to find, I remember listening to the St. Louis Rams and they've got astroturf and their backs are really fast, so the Rams are going to have a real home field advantage. It turns out that you gain no advantage whatsoever with fast backs on astroturf. And you think about it for a second and it's immediately obvious why. The defense gets quicker too, so they can shut you down faster. So basically there's no strategic or tactical advantage to playing on astroturf for anybody. Now I can't comment on field turf because no one's actually done any studies of that. My guess is that field turf and real turf are very, very similar. So that's interesting. We just said that. Okay. I've heard kicking coaches talk a lot about kick it in the sweet spot. I have a more important question, which is how do you get a pair of pants like that? I love those pants. So the idea, I guess, is that the kicker is supposed to kick the ball on the sweet spot. The problem is that a football has no sweet spot. You don't want to kick it on the laces, that's for sure, but that's just because of the symmetry of the kick. It turns out that only things like bats have sweet spots, and it requires, first of all, that somebody be holding one end here, and that you hit it down here at the center of percussion. And the sweet spot is really right here. You can change the position of the sweet spot by where you hold the bat, where you grip the bat, but basically the sweet spot is the point where when you impart an impulse to the bat and it starts to rotate, the back actually rotates anti-clockwise, going to the other side, going to the left, And so momentarily this spot doesn't move. So if you're hitting and you hit the ball on the sweet spot of the bat doesn't move under your hands and give you a sting. There is no analogous property to a football. So the football has no sweet spot. Okay, here's another one. Now let's fill the football with helium. It'll give it better hang time. After all, you think about it, the Goodyear blimp has really good hang time. So let's fill. I notice we have an Ohio State fan in the audience. That's good. This is you think about that for a second, and that's not going to work. If I take a wiffle ball and I take a baseball and I throw them at the same speed, which goes further? The baseball goes further. Why? Newton's first law and Newton's second law combined. It's got more mass, so the air drag doesn't slow it down as effectively. The air drag being roughly the same in either case. And the same is true with a ball filled with helium. It just won't go as far and it won't stay up as long because it's more effectively slowed down by the air drag. There was this infamous, I'm not sure which, study done at Ohio State where they proved that the ball would go about 5 yards further with helium than with air. The problem is they had a kicker and he kicked one ball filled with helium 10 times and he kicked one ball with air 10 times. And it's true that the average was greater for the helium ball, but the difference was about 5 yards and the uncertainty in the measurement was about 30 yards. So effectively there was no difference between the two. Numerical simulations that we've done indicate that you probably get a distance advantage of about an inch and a hang time advantage of about 50 milliseconds filling the ball with air instead of helium. Okay, right. So we did this for a while, and it got some attention. I just want to show you this piece to kind of illustrate what happened here. And this, I know, is a problem. Oh, nope, it's back. Here we go.
Finding about this evening, Science in the Stadium. For some years here, we had a colleague from Nebraska. She was passionate about the news and the University of Nebraska football team, the Cornhuskers. Our colleague had a sense of humor about farm jokes, but she never told us about the physics. For that, ABC's Bob Davison had to go all the way from here to Lincoln, Nebraska.
There's almost nothing Professor Timothy Gay likes more than teaching physics.
We experience time in a completely different way than we experience space.
Nothing, that is, except University of Nebraska football. In football, Professor Gay sees not only the game, but his beloved physics in action. Mass, velocity, force, on display in real life. Professor Gay decided football was a perfect way to make physics understandable and fun. So now, how do you reach a wider audience? With television, of course. A really big television.
Football physics with UNL physics professor, Dr. Tim Gay.
Energy, like force and momentum, are important quantities in physics.
The giant screen at Nebraska's Memorial Stadium now shows Professor Gay's physics lectures. The class size, 77,000. This game, the subject was energy.
Both teams combined expend enough energy to lift the pickup 10 yards in the air, enough for a vertical burst down.
Other video lectures have addressed momentum and force.
Produce momentum roughly 1,000 kilogram meters per second, and 3 times that of the Oklahoma player effectively stops the run.
And gyroscopic motion.
A football must be spinning for it to be stable in flight. I wanted to talk to as many people as possible about physics. I was worried, though, that the fans would say, we come here to see football. We don't really want to go back to school and learn about physics.
The professor needn't have worried. Fans pay attention. And so do the players, including 320-pound offensive tackle Adam Joel.
Not like most things where they show something and not everybody watching it. Everybody's focused on watching it. It was very entertaining for the people.
By season's end, fans may no longer talk about a good punt, but about the angle at which it was kicked, and how the ball then rotated on the proper axis. And if all of this makes the Cornhuskers better, colleges soon may not only have a team physician,
Let's thank our football physics professor for his
but also a team physicist. Bob Jemison, ABC News, Lincoln, Nebraska.
So that's kind of the end of the story, but I do have one other thing I need to take care of before we quit. I've noticed that when I give these talks at high schools and universities, that players from opposing teams come in and try to learn a little bit of the physics too, so that they can win the game. And I know you guys have a big game coming up against the Crusaders on Saturday. So I wanted to be fair, and I wanted to maybe give. I've sensed there are a couple of Crusader spies in the audience. I wanted to be fair, and so I wanted to give them some physics help as well to make the game, a little more even. So without further ado, this is what I think they should know. First of all, the speed of light varies depending on your frame of reference. That's important. Secondly, the electric field equals momentum times the centrifugal force raised to the second power. That's the famous formula, E equals mc squared. And finally, unlike football, a career in physics guarantees high pay, endless partying, and a chance after chance to meet hot dating prospects. And with that, I thank you for your attention.
Students at TLU engage in high-impact educational experiences that include civic engagement, aesthetic expression, critical thinking, and a focus on intercultural knowledge in a community that welcomes the interplay of faith and reason.